Okay, so let's start. So originally I had a different plan for today's class, but just yesterday I came across this paper on archive and thought that this would be a very nice thing to discuss, which kind of complements what we have seen in this particular course. So this was just uploaded, or at least appeared on archive yesterday. It was uploaded on 11th, and it gives sort of a very nice survey of what is known on packed learning models. Of course, it can't cover everything that is known. It focuses only on certain aspects, particularly in terms of an aspect that we didn't focus too much in this course, and more importantly, the computational aspects. All right, so in the first part of the course, when we defined packed learnability, we only focused on the sample complexity of a learning algorithm. What is the minimum number of samples required to obtain an epsilon delta error? Right, but in the original works, which goes back to Valiant, who defined the packed learning framework, he also focused on the computational aspects. What is the computational complexity of learning the algorithm? So it's not just the sample complexity, but also the computational complexity of learning or training, so to speak, for achieving a target epsilon delta error. All right, and this particular paper gives a nice survey. At least it has the main aspects of what is required. So this class will be a little bit different. I'll go over this, at least the salient features of this paper, and hopefully give some insights that we didn't see in the course. All right. So it'll also be a good refresher of at least some of the things that we've seen in the course. Right. So again, going back to what we've already seen, in the setup, we focused on binary classification, which is also what is the main focus of this particular paper, just binary classification with 0-1 loss. And you're given a particular domain or a universe of objects, also called instances, and some classification rule that you have to learn. Now in this paper, the main discussion is of learning a concept class, which means that there is some function to be learned, and the ground truth is basically obtained by labeling points according to some function. Right? So conditioned on the randomness, conditioned on a particular data point, the relationship or how you get the label for a particular data point, it's according to a fixed rule. All right, that's what most of this paper talks about. Okay, so there is some unknown function f, and the goal is to learn this particular function. All right, and so the main focus is not just the sample complexity, but also the running time. So we assume that every base operation, let's say multiplication, addition, division, comparison, all of these takes unit time, and for a given number of samples n, how does the complexity scale with n? Or more importantly, given a particular target epsilon and delta, how does the computational complexity or the running time as well as the sample complexity scale with epsilon and delta? Okay. Yeah, so of course, I mean, all of this, the framework that we have seen in packed learning, it seems kind of natural, but when the initial works, which essentially comes from this particular paper of Valiant, I'm not sure where it's cited. So it was back in 1984 when Valiant introduced the packed learning framework. At that point of time, statistical learning was not so formally defined. All right, so this was a paper that initially introduced the packed learning framework, and a lot of other papers around that time built on this, and that's what we have today. All right, but but one point to note is that the kind of problems and the setup that we have seen is only one particular framework that was originally considered by Valiant. And the original paper considered an even more generalized model where potentially there could be corruptions, or maybe you don't see all of X. So if you think of X as a feature vector, maybe you don't observe all of the features. Some of them are hidden from you. So it also considers situations like that. All right. And we'll also see some other models in today's class. Okay. So the paper looks, yeah. So let's suppose that the domain is the set of all vectors in Rd. Okay. And so far what we have assumed is that the data set consists of points from Rd and the corresponding labels corresponding of each particular point, right? But in the original framework, he considered a slightly more general model where maybe you don't see all of the components in Rd. You only see some subset of the components of each vector.
That is what observation data, right?
Which?
Subset of R probability, let's say. The features function.
Correct. But maybe you don't get to see all of the features. Right? Maybe some of the features are corrupted, they're erased. Okay? So what you get to see is this sort of erased data along with the corresponding labels. So which means that you may need even more samples. So if there's no erasure at all, then obviously you can do better. If there are some erasures, potentially you could require more samples to achieve the same target epsilon comma delta error. All right. So in that sense, that and other ways, the paper looks at more general setups. Okay. And we'll see some other generalizations also later. Okay. So one specific case that we look at is learning the concept class. All right, and it's helpful to go through some simple examples to look at subclasses of functions that can be learned easily using a small number of samples. All right, and this is how it was also historically developed. So in the course, we looked at learning the concept class, but we mostly focused on agnostic pack learning. All right. But agnostic pack learning, as we all know, is much harder than learning a concept class. But historically, the first classes of works were on learning specific classes of functions, simple functions. And one class of functions that this particular review also focuses on are Boolean functions. So the domain is the set of all binary strings of maybe length d, right? And so there'll be two classes of domains that we'll consider. One is the class of all binary strings of length d. The other is set of vectors of length d. And we look at specific concept classes to be learned. All right. So one simple function class are those which can be represented as Boolean conjunctions. So in other words, you can write all functions that can be written as the AND of some subset of the variables. Right? So a function of the form x1 and x3 and x5. That's one Boolean conjunction. All right. All right, and what you get to see is a particular data set where there's a target function, there is actually a Boolean conjunction, and you observe the function values for some subset of the binary strings. All right, but one thing that you could potentially consider, one generalization, is that your hypothesis class could potentially be different from the concept class. Here it's assumed you know what the concept class is, but you could choose to use a different hypothesis class compared to the original concept class. And we'll see situations where the two could be different. Now, there are different reasons for choosing a hypothesis class different from the concept class. For one, it may be computationally easier to choose a hypothesis class that is different from the concept class. And sometimes maybe it's easier to learn that hypothesis class could potentially approximate the concept class well enough. And maybe the concept class itself cannot be learned, or we don't know how to learn it efficiently, but the hypothesis class can be learned exactly. All right. So a packed learning algorithm, the definition now is a little bit different from what we saw in class. So packed learning algorithm for a particular hypothesis class, for a concept class C and a hypothesis class H, is one where the algorithm takes m samples. M can be a function of n, epsilon, and delta. So slight difference in notation over here. N is the size or the dimension of the domain. So we're looking at binary strings of length n. That's the domain. And it takes m samples as input, and it has runtime t, and it outputs a particular hypothesis or a predictor which has a probability of error at most epsilon, and this happens with probability at least 1 minus delta. So it's essentially the same definition as we had in class, except now that the runtime has to be some function of n, epsilon, and delta. All right. So let's look at this specific concept class, which is learning Boolean conjunctions. All right. So the AND of multiple of some subset of the variables. All right. And here is one particular algorithm that works very well. And it's a natural algorithm to consider. So you observe a set of samples, which is you have binary string and the function value. All right. So since you know, so every function basically looks something like this, right? It is maybe x1 and x2 bar and x3 and x5 bar and so on, where by bar I mean the complement, right? So the observation that they make is that suppose you observe a sample 0 1 0 1 1, and the AND or the function value for this is 0, right? What can you say? What kind of functions can you eliminate? Correct. So if the function value is equal to 0, then it means some combination of these variables should give you a 0. All right. So if x1 is equal to 0, then can the function value ever be 1? Okay, so let's take two cases. One. All right, so one of these. Okay. Yeah. You can't say it right away. But let's suppose that you know that the function that 0 1 0 1 1 maps to 1. Okay. Then what can you say about the contribution of the individual variables?
Is this a different kind of sample or the same?
So I'm just trying to see what you can say for a particular input. So maybe let's just simplify. Let's just take 0, 1, 0 gets mapped to 1. Okay. So for any input where x1 is equal to 1, can the output be 1? Okay, for any input string where x1 is equal to 1. So in this case, x1 equal to 0, x2 equal to 1, and x3 is equal to
So you can say that the function won't have x1 and x3.
the function will not have x1 and x3 in it. And why?
Because they would be equal to 0. What if 1 maps to 1? In that case, x1 equal x1 and x3 information is not sufficient. There is a training sample exists 1 1 1 which maps to 1.
So sorry, can you repeat?
So if I have a training sample 1 1 1 which maps to 1, from that information I will say if x2 is 1 and remaining options are eliminated.
Okay.
I was saying, I'm trying to say, so with one training sample, it may not be sufficient to say, but from this, I can eliminate those if x1 equal to 1, x2 equal to 0, x3 equal to 1.
x1 equal to?
I'm just eliminating those which are exactly complement to this.
You're eliminating those which are complement to this, right? So x1 equal to 1, x2 equal to 0, and x3 equal to 1.
Yes.
That can be eliminated, right? So basically the idea is similar. So if you observe any particular positive sample, then you can successively eliminate some of these literals which give an evaluation of 0, right? So for example, suppose you got x, so 0 1 0 gives you 1, and now let's say that 0 1 1 gave you a 0. All right, then now what can you say?
So if x3 equal to 0 maybe 1, x3 equal to 1 maybe
X3 equal to 0,
is 1, x3 equal to 1 is 0. So I will still
Okay.
eliminate x1 and x2 complements.
you will eliminate. So one thing is that the function clearly depends on x3,
Yes.
right? And the function can be 1 only if x3 is equal to 0, irrespective of what happens to all of the other variables. Do you agree? Right? No? Yes or no? Okay. So which means that from just these two samples, I can say that x3 must be equal to 0 for the function value to be equal to 1. Right? Which means that now I have fixed one particular value or one of the literals, x3. All right. So essentially, for any x that gives you 1 as the output, you look at the remaining strings and see which of the remaining strings gives you a value of 0. So wherein one of the variables is different. All right, and then you try to eliminate those particular variables. Again, the simplification over here is that the function is just the AND of some of the variables and their complements. Okay? And that's it, that's the algorithm. You do nothing else. Okay? And how many samples do you draw? Let's suppose that you draw a number of samples which is order 1 over epsilon times n plus log 1 over delta. Okay, let's suppose that you do this. Then it turns out that this particular algorithm achieves a probability of error of at most epsilon, and this happens with probability at least 1 minus delta. And the reason really is because this algorithm is consistent, or in other words, it achieves zero empirical risk. You can show with just a little bit of thought that this is in fact an empirical risk minimizer, and more importantly, it achieves an empirical risk of zero. And that's a rather important observation. So if there exists some algorithm that works in polynomial time and it achieves zero empirical risk, then these many samples are essentially sufficient. All right. So you take any finite concept class C. All right. And suppose that you have one empirical risk minimizer that achieves and that is guaranteed to achieve zero empirical risk. So irrespective of what data set you observe, suppose that you have one computationally efficient or even otherwise empirical risk minimizer that achieves zero empirical risk, then the sample complexity or these many samples are enough to achieve epsilon delta error. And that's a result. All right. And since the algorithm that I just described earlier achieves zero empirical risk and can also be done in computationally efficiently, this class of Boolean conjunctions is path learnable in time that is polynomial in n and 1 over epsilon and log 1 over delta. And the number of samples required is also polynomial in n 1 over epsilon and log 1 over delta. All right. So one thing is that if you think about our analysis of empirical risk minimization that we did in class, effectively in all cases, we showed that the sample complexity is polynomial in 1 over epsilon and log 1 over delta. All right. But we did that using a completely different approach. We didn't really care about computational complexity. We just looked at the empirical risk minimizer and showed using concentration inequalities that these many samples are sufficient. So this is another way to look at it. It gives you something a little weaker, but at least for Boolean conjunctions, this also tells you something about the computational complexity of learning. All right. And in fact, this is kind of the best that you can do. So in general, you can always obtain if the focus is only on sample complexity and you don't care about computational complexity but rather sample complexity, the accuracy parameter can be made to depend on which is polynomial in 1 over epsilon and log 1 over delta. All right? As long as it is learnable, right? As long as the hypothesis class is or the concept class is pack learnable, the dependence on delta and epsilon is just order log 1 over delta and polynomial in 1 over epsilon. And one way to approach this is this. In some sense, it's a boosting technique, but in another way, it can also be interpreted as a model selection technique. Basically, what you do is, well, suppose you have an algorithm that achieves accuracy of at least 1 minus epsilon by 2, and with some probability, right? Then basically you take your n samples, your m samples, you partition them into chunks of size log 1 over delta, all right, such that with probability at least 1 minus delta by 2, at least one of the hypotheses is guaranteed to give you, is going to kind of estimate the actual accuracy, all right. And you use the last, so you divide the m samples into small chunks, let's say m prime chunks. For the first m prime minus 1 chunks, you do some kind of empirical risk minimization, or you run independent copies of the learning algorithm. So you get m minus 1 hypothesis, or m minus 1 or m prime minus 1 predictors. And you use the final m prime chunk to evaluate, loosely speaking, to evaluate each of these predictors in some sense. All right? And using these small additional number of examples, you can actually estimate the accurate, so you have m prime minus 1 predictors that you got using the first m prime minus 1 chunks. And you evaluate each of these m prime minus 1 predictors on the last chunk. So in some sense, this is like using a validation set. All right. So effectively, I have m samples which I split into chunks. Each chunk is of size order log 1 over delta. All right. Now, from each of these chunks, I will generate a predictor. Let's call them H1, H2, up to H. Let's call them Hm prime. So I have m prime predictors. Let's say that for over each chunk, I did empirical risk minimization. Depending on the realization of the samples within each chunk, I could get a different predictor, right? But now I want to choose that predictor which gives me the least generalization error, right? That's the end goal. And I know that these predictors achieve a probability of error that is at least less than half minus epsilon. That's the guarantee that I have. The goal is to basically treat this as a validation set, which means that I'm going to find the empirical risk of each of these predictors on this particular validation set. All right, that's it, nothing else. So I have a separate validation set. I train these m prime predictors and choose that predictor which gives me the best performance within the validation set. Now that will achieve a probability of error of at most epsilon. All right. It requires a little bit of analysis. It's not too hard. And I think I gave a similar type of a question in the assignment. So you can look at that in a little more detail. All right. So in other words, for any concept class that can be learned, even if it is weakly learnable, if it can be learned, then you can achieve any epsilon comma delta error using a number of samples that is polynomial in 1 over epsilon and in log 1 over delta. So either it's not learnable or it's polynomial in 1 over epsilon and log 1 over delta. So you'll never need a number of samples that is, say, exponential in 1 over epsilon or polynomial in 1 over delta. All right. But then the dependence on n, that is the dimensionality of the domain, can depend. It may or may not be polynomial in the dimension of the domain. So if you want to achieve polynomial complexity, so some classes could be learned polynomial in n, some classes may not be learned polynomial in n. All right. So basically, the takeaway is that if the concept class can be learned, in other words, if the VC dimension is finite, then the sample complexity is always going to be polynomial in 1 over epsilon and log 1 over delta. But this may or may not be polynomial in little n, the dimension of the domain. All right. But on the other hand, the computational complexity can depend, may or may not be computationally. So the goal is to understand what is the computational complexity of learning. All right. So a large body of work has gone into understanding which classes of Boolean functions can be efficiently learned. We've seen that Boolean conjunctions can be efficiently learned. So any function that can be written as an AND of multiple literals can be learned efficiently. And if you can do it for AND, you can also do it for OR. Right? You just take complements. So the complement of AND of multiple literals is just the OR of the complements. Right? So if you can learn AND, you can also learn OR. But what about more general functions? Right? So if you want to generalize that just one step further, going from just AND or just OR to more complicated Boolean functions, well, we know that any Boolean function can be written as either in the disjunctive normal form or conjunctive normal form, or in other words, you can write it as an OR of multiple AND literals, AND terms, or AND of multiple OR terms. But the number of terms in each OR or each AND expression could be arbitrary in general. All right. So let's look at a restrictive class, a smaller class of all possible such functions. So a KCNF formula is basically an AND of width k disjunctions. So you take k variables, any subset of k variables, take the OR of those, and then you take the AND of such terms. All right, so it's an AND of multiple terms, and each term has exactly k variables. All right, but the number of such terms could be arbitrary. The only restriction is how many variables can be in each AND term, and that is k. All right. So it turns out that this can be handled using the same approach that we just discussed. So a KCNF formula is basically is something that looks like this. Right? So each term is an OR of two terms. Right? And one way of learning this particular algorithm is you treat each of these terms as a single variable. All right, but it's not a Boolean variable, but rather as a vector. So you treat each variable or a meta variable as they call it in an expanded feature space. So you look at all possible configurations that each term can consist of. Right? So let's take one particular term. How many possible ways are there of generating one of these terms? So each of these terms is some xi or xj, or it's some xi or xj bar, or xi bar or xj, or xi bar or xj bar. It can only be one of these combinations. All right. How many ways are there of choosing this? So if you look at each disjunction, right, each of these terms, among n, if you have n variables, total of n variables, how many possible such configurations can you generate? For each term, for one such term. NCK? Not how, okay, so not how many values this can take, right? How many distinct functions can I generate in this particular form?
I'll fix x4 and x6 and I'll just take a combination of all this.
No, so how many different functions are possible for just this term?
4n square, 2n whole square.
Why 2 and the whole square?
Because there are 2n ways of choosing the first one.
Correct. There are 2n ways of choosing the first one, and not exact. You don't have 2n ways. 2 times n minus 1 ways. Because once you choose a variable for one, you choose a different variable for the second. All right. Fine. At most, so if the total number of such functions I can generate is at most 2n square, because basically I pick an I pick a j. The only flexibility is in picking an I, picking a j, and whether it's complement or uncomplement. Right? So there are 2n ways of choosing the first term and 2n ways of choosing the second term. The first term can be either x1, x2, x3 or xn, or it can be the complement of these. And the second term can also be x1 up to xn or the complement. All right? So in general, for a fixed k, the number of possible disjunctions, the number of possible k disjunctions that you can generate is 2n to the power k. That's it, right? And if k is small, then this is just polynomial in n. All right? So So the elimination algorithm that we looked at previously can also be used in this particular context. And you can also show that if k is fixed, then KCNF, and similarly the disjunctive normal form, which is an OR of AND terms, can also be learnt in time that grows as n to the order of k. All right. So if we look at KCNF formulas or KDNF formulas, then these can be, there exists a simple algorithm, simple in the sense that it's simple to describe, simple algorithm that can be, that operates in time that grows as n to the order of k. If k is a constant, then this is polynomial in n. But if k is also allowed to grow with n, then this is no longer polynomial in n. So now we've seen we're kind of expanding the class of functions that we can learn efficiently. All possible disjunctive forms can be learned efficiently in polynomial time. All conjunctive forms can be learned in polynomial time. And KCNF and KDNF formulas can be learned in polynomial time, assuming that k is a constant. So what happens if k is not a constant? Certainly this algorithm doesn't work, right? Because in this algorithm, k, if you take k to be polynomial or whatever, k to be growing with n, then this is no longer polynomial in n. All right. So it turns out that it's impossible to do any. So this is a simple algorithm, right? And it turns out that you can't really achieve a computational complexity that is significantly less than this. So one can show that it is impossible for any pack learning algorithm for KCNF to have a sample complexity that is n to the something that vanishes as for large k. All right. So for example, you can't achieve n to the log k time complexity. However, this doesn't work for KDNF formulas because that turns out to be a more complicated. All right. So that's one particular approach. So that's one class of functions that we can or cannot learn efficiently. We'll come back to this KCNF and KDNF again, but that was the concept class, and the goal was to learn the concept class itself. In this case, the hypothesis class was equal to the concept class. All right. Now let's look at and the approach for empirical risk minimization, or the learning algorithm that we considered so far was this elimination type of algorithm, right? Where you see all of those configurations which align or which are consistent with the kind of outputs that you want to generate, and then eliminate those that are not inconsistent. A completely different approach is using decision lists and decision trees. So what do you mean by that? So one way of generating a disjunction or a conjunction is the following. You can represent the function as sort of a decision list. And what is a decision list? So any function can be written in this particular form. So this is basically a tree with each node being a variable or its complement. All right, and the leaves are all the labels, either +1 or -1. So you evaluate the function by going through this decision tree from the root all the way up to a particular leaf. So for example, let's take x3. So the root is x3 bar, So if x3 bar is equal to 1, you proceed to the left. If x3 bar is equal to 0, you proceed to the right. So if x3 bar is equal to 0, then you just output 1. If x3 bar is equal to 1, then you go to the left. Okay, I think it's the other way around. If x3 bar is equal to 1, you go to the right. If x3 bar is equal to 0, you go to the left. All right. So if x3 bar is equal to 0, then you check what is the value of x2 bar. If x2 bar is equal to 1, then you output -1. If x2 bar is equal to 0, then you check x7, and so on. All right. So you evaluate the function by making this sequence of binary decisions. You look at one variable, see the particular value, and then traverse either to the left of the tree or to the right of the tree. All right. So something of this form is called a decision list, but then you can have more complicated decision trees. All right. Wherein in a decision list, one side always gives you the output. It gives you an output label, and one side gives you another variable to check. But a decision tree is a more generalized version where it's just you keep checking one variable at a time. Right? In both these cases, the leaves of this tree correspond to the final labels that you generate. Okay. So now so to represent, so the question is what kind of Boolean functions can be learned efficiently? One way of representing a Boolean function is as a KCNF or a KDNF for arbitrary k. Another way of representing a Boolean function is using decision trees. All right, so if we are able to learn maybe all possible decision trees efficiently, it means that you can learn all possible Boolean functions efficiently. Because any Boolean function can be represented as a decision tree. But obviously it's not possible to learn all Boolean functions efficiently. So the question is, what classes of decision trees can be learned efficiently? And if you think about it, if the function is, as we've seen previously, complex functions can't be learned efficiently. Which means that if the decision tree is too large, that is, it involves too many variables, then you should not be able to learn it efficiently. All right? And indeed, that is true. So ultimately, it depends on how do you measure the complexity of a particular decision tree, and here are some parameters that capture the complexity. One such measure is the rank of the tree, which is the maximum depth of a complete 2 to the r leaf binary tree that is contained in the tree. It's just some measure of complexity of the tree. All right, and it turns out that there's an algorithm that runs in time that is polynomial in M and polynomial in N, but the degree of the polynomial is R. So in other words, if R is a constant, that is your function, your Boolean function, can be represented as a decision tree of constant rank, then you can learn it efficiently. All right. So any size S decision tree can be learned in time that is, so by size S, it means that the number of leaves is S. All right, and so there exists an algorithm which has runtime n to the order log S, and that helps in packed learning the class of decision trees. All right. So now we've seen two different ways of learning two different classes of functions. In the case of DNFs or CNFs, or KCNFs or KDNFs, one approach was this elimination technique, and now for the class of decision trees, there's some other approach. Let's treat that as a sort of a black box.
Eventually, both the approaches are same. So, because the first approach,
Yes,
the first we are just eliminating all those.
correct.
It's something like you are fixing one variable and looking at the other variables too. So
Correct.
you are traversing in the same way in the tree as well.
You're traversing. It's conceptually a little bit different. It's subtly different. That is, the learning algorithm for the decision tree would not be the same as just the elimination technique. All right, but it's still sort of a greedy algorithm. All right. So a completely different. So the goal is to see what kind of functions can be pack learned efficiently, and hopefully to use these to learn even more complicated classes of functions. All right. So one is KCNF and KDNF. The other is decision trees, all of sort of constant of small size. Another approach is those functions that are linear. All right. So you solve a system of linear equations to, or in other words, a set of parity functions. All right. It's a different class of functions where every function in the class can be written as an XOR of some of the variables. That's what is a parity function. All right. And any parity function can be learned efficiently. And the reason is you have Gaussian elimination. All right. So pack learning amounts to just solving a system of linear equations. As long as you have sufficiently many linear equations, you can recover the variables exactly. Right. And that's all that is there over here. And since you can do Gaussian elimination to recover the parity, you can use the same approach to also recover polynomials over the binary field. All right, because effectively a bunch of polynomial equations can be written as a bunch of linear equations. So if you take any set of polynomial equations, say a0 plus a1 x plus a2 x square and so on, plus ak x to the k equal to y. Now this is polynomial in x, right? But x is anyway the variable. The quantity that we're interested in recovering, since we want to learn the polynomial, the quantity that we are interested in recovering are a0, a1, a2 up to ak. So we are given x and we are given y, and our goal is to recover a0, a1, a2 up to ak. The advantage is that this, although it's polynomial in x, it's only linear in the vector a. Right? This can be written as an inner product between a0 up to ak along with 1 x square up to x to the k. All right. And since it is linear in a, solving for a just amounts to solving a system of linear equations, which you can again do using Gaussian elimination. So it means that the class of polynomial functions of degree k over f2 can also be learnt efficiently, and the computational complexity is just n to the order k. So all constant degree polynomials can be learnt efficiently. right? So we're trying to build the class of functions that we can learn efficiently, right? Another class of functions that can be learned efficiently, something that we've already seen in class, is the class of all linear classifiers, right? So we've seen that the hard SVM algorithm, for example, it's a pack learning algorithm for linear classifiers, or RD in fact, right? And in fact, linear classifiers and more generally polynomial classifiers can also be used to learn Boolean functions. So a linear threshold function is basically just a linear classifier. So it's f of x is equal to sine of L of x, where L of x is just an affine transformation of x, right? And we've already seen in class that linear threshold functions can be pack learned in polynomial time because it just amounts to solving a linear program. And using the same approach as we just discussed, if you can learn linear classifiers, you can also learn polynomial classifiers. So any function that can be written as sine of p of x, where p of x is a degree k polynomial. Right. So this also means that if you can approximate your target function as a degree k polynomial, so your function may not be a polynomial, but if it can be closely approximated by a degree k polynomial, then you can also learn that function, that class of functions using this particular algorithm. Because now your concept class may be much richer than the class of degree k polynomials. But you can choose your hypothesis class to be a degree k polynomial, and hopefully the approximation error is going to be small. Right? So now you decompose the generalization error in terms of the approximation error and the estimation error. Now you know that for polynomial classifiers, you can make polynomial or linear classifiers, you can make the estimation error small. But ultimately, if your concept class is different from your hypothesis class, then it depends on what the approximation error is. And if your function can be well approximated by a degree k polynomial, then it means that the generalization error can also be made small. Right? So it turns out that this particular tool has also been used extensively for learning KCNFs and KDNFs. So although your goal is to learn, let's say, a KCNF, you try to approximate the KCNF by a polynomial classifier and then try to learn the polynomial classifier instead. Right? So there's a result which said that any DNF formula with S terms can be expressed as a polynomial threshold function having degree which is order n to the 1/3 times log of S. And since you can learn polynomial threshold functions or polynomial classifiers efficiently, you can also learn S-term DNF formulas in a time that is not quite polynomial in n, but not exponential in n either. So this is quasi-polynomial, which is sub-exponential in n. All right? And you can also approximate decision trees. You can try to approximate a decision tree using, again, a polynomial classifier of some particular degree. And therefore, you can show that the class of all degree S Boolean formulas, all size S decision trees, can be pack learned in this particular time. So these are different techniques to show whether you can efficiently or inefficiently learn a particular concept class. Right? So a very popular approach is to approximate the class of functions that you're interested in learning by using polynomial threshold functions or linear threshold functions. And since you already know that polynomial threshold functions can be learned efficiently, this implies that you can also learn the particular concept class efficiently. All right. Right, but of course it's not a silver bullet. You can't use it all the time. So there are there's also a rich literature to see what kind of Boolean functions cannot be expressed by well expressed or well approximated by polynomial threshold functions. All right. Okay, so that was mostly about. I mean, there's a lot of other detail in the paper, so I encourage you to go through it a little carefully. But that was one particular model of learning. Right? The model of learning that we've seen is you receive n independent samples, a training set, and then you learn using those n independent samples. But in practice, you can also consider other learning models, wherein you either have more resources or perhaps the distributional assumptions could be different. So one popular approach is this pack plus membership queries model, wherein you observe a training data set, but then at the time of learning, you're also allowed to ask questions. The learning algorithm is also allowed to ask certain questions if it so requires. All right. So basically you want to learn a target function f, you receive say m samples, but the learning algorithm is also allowed to ask, after looking at these m samples, it's allowed to ask questions of the form, what is the value of f of this particular string? Okay. So the data set consists of random strings and their function evaluations. But in addition, the learning algorithm is also allowed to ask what is the value of the function on specific strings that it wants to find. All right, and hopefully this can only help. Right. So for example, at the very extreme, instead of observing m random observations, suppose you are allowed to ask m random, or the learning algorithm is allowed to ask m queries. Right? What is the value of f of 0, 0, 0, 0, 0? What is the value of f of 0, 0, 0, 0, 1? And so on. Right? So it's allowed to ask such queries as well. It's sort of the following: you observe n samples, but you're also allowed to interact with a teacher who can answer such particular queries. And asking queries can only improve the performance of the learning algorithm. So in this context, unlike the standard pack learning framework that we've seen previously, in the standard pack learning framework, if you want to achieve zero probability of error, right, that may be impossible using a finite number of samples, right? Because there's a possibility that you never see the entire space in m samples for any m. So if you are allowed to see the outputs of all 2 to the n strings, then you would be done. You don't need to do anything more, right? Because you get the evaluations of all of those 2 to the n strings. But then with non-zero probability for any m, you don't see all of the 2 to the m strings. So there is still some uncertainty on what the actual function is, right? There's some non-zero probability that there is still some confusion at the end of m samples. But on the other hand, if you are allowed to ask queries, then at most 2 to the n queries are sufficient, right? Because in principle you can ask, okay, what is the value of f of all zeros, f of 0001, f of 0010, and so on. So with just 2 to the n queries, you can find the function exactly with zero error. All right. So, and there are various other kind of such query models that are also studied. And a lot of results are known as to what functions can be learnt efficiently and what kind of functions can't be learnt efficiently in this particular model.
How do we decide what queries to ask?
So that depends on the query model. What kind of queries are allowed, that you're allowed to ask. And there are different models that are studied in the literature. So one is the so-called membership query, which is you ask what is the value of f of x for some particular x. You can also ask equivalence queries in some sense, wherein the learning algorithm is allowed to ask, is allowed to say output some particular h and ask, is h equal to f? All right, or h is equivalent to f, and this oracle tells you yes or no.
Would that not be computationally very expensive?
Which
Like finding the edge for all the samples again and again and seeing if it is not
potentially, but the goal is to design an algorithm that doesn't ask too many queries, maybe a small number of queries. So for example, after seeing the m samples, right, now there may be a confusion among a small number of functions potentially, and now if you're allowed to ask equivalence queries, is it equal to this or this or this or this, then you can potentially get zero error, because now you have just a small list of functions over which you have to distinguish, and for those you can ask the query and distinguish between those functions. All right, so those are the sort of general ideas that are used. Okay, so another different learning model is the following. So what we saw was sort of the agnostic learning model, where there's some distribution pxy, with the relationship between x and y. It could either be deterministic or it could be random. But the fundamental assumption was that x1, x2 up to xn are all IID. The distribution could be chosen arbitrarily, but conditioned on this distribution. An adversary could potentially choose the distribution, but given this distribution, the samples are IID. But then you can look at other models as well. So one such model is the malicious noise model, wherein you assume that with some probability, the sample that you get, or some fraction of the samples, are drawn according to this IID distribution, which is unknown. But some fraction of the samples could be corrupted, so they don't come from the distribution, from the same distribution as the rest of the samples. And an adversary can put in anything it wants. It can fill these data points with arbitrary values. All right. So that's the malicious noise model, and there are results known in this particular case. And in particular, some early and recent works also show that using linear threshold functions, you can tolerate a noise fraction of eta, which is roughly log s by s, where s is the number of samples required by the original polynomial time packed learner. So if there is a polynomial time packed learning algorithm that works without malicious noise, then you can also handle malicious noise by increasing the number of samples. Effectively, that's the result. All right. Agnostic learning is something that we have already seen. So, in fact, yeah, that's what we've seen earlier, seen in class. But another sort of rich body of work is in the case where there is random classification noise. So in other words, there's some deterministic function, f, that relates the input with the output. But what you observe is not f of x. It's f of x plus some noise. So maybe for some of the samples, the value of f of x is flipped, independently of everything else. All right, and there are several variants of this particular model that are known. One very popular variant is the statistical query model, where the learning algorithm can't ask membership queries, but it can potentially ask the statistics of certain functions. It seems like a very artificial setup. You would wonder how you can get statistical queries. And the statistical query or SQ model is very frequently used to derive lower bounds or to find out when something cannot be learned. This can be done in various problems. All right. So in all of these cases, the assumption is that the input distribution is arbitrary and it is unknown. But there's also a good body of work where the distribution on the inputs is known. So in some sense, this is an easier setting because you know what the input distribution is. And very frequently, the input distribution is either assumed to be IID across the components or maybe uniform over some particular set, or let's say something like a Gaussian. It's usually some simple distribution. All right. And even in these cases, it's known that assuming this fixed input distribution makes the problem a lot easier. So for many problems where it's hard to prove results in the distribution free setting, it is possible to prove nice results in the distribution specific setting. All right. And one very popular technique to analyze this uniform distribution setting is using the theory of Boolean functions, where you use the Fourier representation of a particular function. So you're given any arbitrary Boolean function. So the input is set of all binary sequences of length n. The output is a binary value +1 or -1. So any function, any such Boolean function has the following Fourier transform representation. So it can be written as a sum over all possible subsets of 1, 2, 3 up to n of the Fourier coefficient corresponding to that particular subset times the product of the elements. All right, the product of the literals that belong to that particular subset. You may have seen the Fourier transform over R, right? The Fourier series or the Fourier transform. There's a more general theory of Fourier transforms for more abstract sets. So instead of choosing the domain to be R, you can choose, say, RD or the set of all, or the Boolean space, the Boolean hypercube to be more precise, or you can also generalize it to arbitrary abelian groups. All right, and there's a rich theory of Fourier transforms for such abstract sets. And using this, you can also devise efficient learning algorithms. So instead of learning the Boolean functions, you try to learn these Fourier coefficients. All right, and if you can approximate the function well using a small number of Fourier coefficients, then you can learn the function well enough. All right. So effectively, all of these ideas look for different representations. And if you can learn simple functions efficiently, then you try to build on that to be able to learn more complicated functions. All right. So basically, if any concept can be approximated by a low degree polynomial in some weak sense, then you can also design a pack learning algorithm for a particular distribution. All right. Yeah. So there's much more, and this particular approach allows you to say something about the pack learnability of various complicated functions, including decision trees as well as SDNF formulas. All right. So these are statements that sometimes you cannot make without distributional assumptions, and also things that you can't prove using other approaches. All right. All right. And there's also pretty nice descriptions. So all of this that you've seen so far were sort of positive results. When can you learn a function computationally efficiently? The converse results are when is it impossible to learn certain classes of functions efficiently. And many of these do make some assumptions on, let's say, a statement like NP not equal to RP, where NP is the class of functions that can be verified in polynomial time, and RP is the class of functions that can be class of all randomized functions that can be evaluated in polynomial time. Right? So the kind of results in this area are assuming some computational hardness assumptions, something like P not equal to NP or NP not equal to RP. You can say that there is no polynomial time pack learning algorithm that learns H efficiently. All right. And there are various such results known for these very specific functions, KDNFs, KCNFs, and so on. All right. But there are also results known where even without such assumptions, you can still prove hardness results, particularly using the theory of pseudo-randomness. Maybe I don't want to say much about this particular thing. But maybe one last point I want to make is sort of the connections between cryptography and learning theory. So cryptography, basically, to design a crypto system efficiently, some of these problems are equivalent to showing that certain functions are easy to compute, but certain functions are hard to compute. So for instance, if you take a public key crypto system, it means that you want to design a function which is easy to compute in the forward sense, in the sense that if I give you a message, there's a function, a polynomial time function which encrypts this function, but without some additional information, it is impossible to or there's no polynomial time algorithm to decrypt the message if you know only the encrypted text. All right. And so this is something that is extensively studied in cryptography, and many of those results can be borrowed to learning theory, and it is this class of functions which cannot be learned efficiently. So if you want to look for classes of functions that can't be learned in polynomial time, then the most natural choice of functions to consider would be those which correspond to crypto systems. All right. And there's a rich theory behind that as well. But also, many such hardness results in learning theory have also been used to design crypto systems. So for example, there's a famous problem on learning parity with noise. So essentially, agnostic path learning in many settings is computationally hard. All right, and many of these results that originated from the learning theory / complexity theory literature have also in recent times been used to design crypto systems that are even hard for quantum computers to break. All right. So two very famous problems that are used in designing such crypto systems are learning parity with noise, and the other is basically lattice-based cryptography, which is that if finding the closest lattice point for a given from an arbitrary point is also computationally hard. All right. So maybe I'll stop here. There's a lot more in this particular paper that I haven't covered in today's class, but that sort of gives you at least a high-level overview of the kind of the flavor of results that are known in the literature, and also a number of problems, a number of open problems that are present even for these simple classes of functions. Right? Even for, let's say, KCNFs and KDNFs, not everything is known. All right, particularly when K is something that grows with N. All right, and all of this was mostly from a complexity theory perspective, but many of these ideas have also been used to construct efficient algorithms that are used in practice, boosting for one. All right. Okay, so maybe I'll stop here. Are there any questions? Okay.